So, this is where we had stopped our discussion. How do you stretch a pulse? And so far we have discussed the simplest possible geometry using a single grating, couple of plane mirrors and a concave mirror. And we had said that if you want a greater stretch, a greater chirp, then you need multiple passes more often than not. As we discussed, if you really want a 200 picosecond pulse, the path difference would better be something like 6 centimeter. So, either your stretcher will be very big, which you do not want, or you have to do multiple passes so that the effective path travel is much more. Okay. So, that leads us to little more complicated geometries. This geometry is called 3C geometry. I am not very sure what the correct pronunciation of 3C is, but then let us just call you that. So, here what you have is you do not have one grating, rather you have two parallel gratings. And I have not animated this slide, but you can see, right, it comes in, similar kind of separation takes place, and then it comes here, comes in. Now, the path has increased a little bit. And again, by 3C geometry, you can make not only a pulse stretcher, but also a pulse compressor. In fact, in the laser that I used as a postdoc, this was the geometry for the compressor. The earlier geometry was the one for a stretcher. Now, more components you have in a system, more parameters you have that you can control and get an accurate match, but more complicated it also becomes. Okay. Next, let us okay, we have already said this, but let us say it again. So, if you put in an uncharped pulse, uncharped input in any of these geometries, then you get a charped output and you get a stretcher. You put in a charped input, the output is uncharped, then you get a compressor, provided the charp that was there in the original pulse is exactly compensated. This is perhaps the 8th time I have said it in the last module and the present one, but this is something that we should never forget. Okay. So, if you have a negative charp in stretcher, generally you want to give a positive charp in compressor and vice versa. So, different people prefer different things. Some think it is better to have positive charp in the stretcher, negative charp in the stretcher. Some feel it is the other way around. So, it is completely dependent on what you want to do. All right. Next, move on to another geometry, which is known to be quite a good one. It is quite popular. It is called Martinez geometry. In Martinez geometry, once again you have two gratings, but unlike in 3C geometry, the gratings are not parallel. If you produce them, they would make an acute angle. And another thing that is very important is Martinez introduced a telescope between the two gratings. It is not as if this geometry is not used. Actually, you get a good amount of stretching using this. But can you tell me what could be a possible problem in Martinez geometry? You are using lenses, right? So, you are making a short pulse travel through a lens. So, that itself introduces some charp. So, the question is, are you using good lenses or not? If you use very good quality lenses in the telescope, then actually Martinez geometry works fine. But one needs to be careful about that. It is not such a big problem, because in any case you want to stretch. So, I am sure you do not want to use it in a compressor, but in a stretcher this works, and in fact Martinez had shown that the efficiency of this geometry is quite good. And one difference between the earlier geometries that we had discussed and this one is that here in Martinez geometry you end up introducing a positive charp. Okay. The gratings are facing are almost at an acute angle. Okay. Next, let us move on to something that is a little more complicated, and this complicated arrangement is called an Offner triplet. Okay, this is one slide that I should have animated, but it would have been too much of work as well, so I did not. So, let us see if we can understand understand what is going on here. What do we have? Here, unlike the other geometries, this looks like a more complicated arrangement, right? Because first of all, you have a plane mirror, then you have a grating. After the grating, you have a concave mirror, followed by a convex mirror, followed by this HRR. Does anybody know what HRR could mean? Well, there is a VRR. So, H and V would mean horizontal and vertical respectively. Yeah, these are called roof retroreflectors, and so this is what they look like. And usually these are very good because already the angle between the two reflecting planes is defined. So, you cannot really mess up things there. It is so we have something like this in the retroreflectors in our spectrometers. In our case, we have 3 sides of a cube. This is sort of a hollow cube, and the coating can be different. It can be aluminum, can be gold, can be dielectric, can be nothing. So, it depends on what you need. So, this is a horizontal roof reflector, this is a vertical roof reflector. So, what is happening? The input comes, hits this mirror and comes to the diffraction grating. This number 1 is the first spot on the diffraction grating. Then where does it go? It goes to the concave mirror. From concave mirror to convex mirror. From convex mirror back to concave mirror, and from there it goes back to the diffraction grating once again to form point number 2. From here the beam goes to a vertical retroreflector, and of course, if it is a vertical roof retroreflector, and if it is a retroreflector, of course, it has to send it back. And good thing about retroreflectors is that the incoming and outgoing beams are parallel to each other, opposite direction, but parallel. So, it comes back and hits the diffraction grating here at point number 3, goes straight to the concave mirror, from concave mirror to convex mirror, then back to the concave mirror and back here in point number 4. From there it goes to the high reflector horizontal retroreflector, and then it goes out. What is the need for such a complicated arrangement? We have actually provided the answer already. In one of our earlier discussions, we have given you the answer. What is the need of such a complicated arrangement? Remember, we had said that if you want a good amount of charp to be introduced, then the path length would better be large. So, here path length is large without the stretcher having to be too large. Okay. If you suppose you had only this mirror, concave, this plane mirror, concave mirror and grating, you can understand path length would have been maybe 1/5 or 1/10 of what it is in this arrangement, right. So, this is basically a geometry in which a lot of passes are made, so that the effective path length is significantly large and you can get a good amount of charp introduced. And the reason why I give you trouble with this kind of a complicated geometry is that in the laser that we use, the stretcher is you can say a modification of this Offner triplet arrangement. Thankfully, it is not as complicated as what it is here, but we will see what it is. But before going there, you must have noticed that we have listed references of papers there. If you are interested to study more, all you have to do is go to these references and you will get leads to further detail about these things. And again, before moving on, I am sure you can understand how much of effort would go in to design something like this. It is not easily done. In earlier days, everybody worked with homemade lasers. Typically, those lasers would be bulky. Even now, for some applications, you have to make your laser. Typically, the laser would be bulky because it is difficult for us to do things that are very complicated, and also we do not want to do it because maintenance is an issue. But in commercial systems, the design is complicated, and nowadays, at least up to this part, generally nobody has to do anything themselves, but still it is important that you know, as for all you know, somewhere sometime you might have to make your own apparatus where this understanding would come handy. Okay, with that we move on to the laser we have. We have a one box coherent Libra laser, Libra amplifier. We are going to talk more about the amplifier in one of the subsequent modules. But for now, let me just show you the ray diagram for a stretcher. And you can already see the complication. Look at the input. The trouble starts here. The input goes through two mirrors that are like this. Okay. And this thing is important if you ever have to align the laser yourself, or if you ever have to even see whether the stretcher is working properly or not. So, let us see what happens. This here is the input, comes through SM5, SM6. So, in Libra user's manual, SM means a mirror which is in the stretcher mirror, and the number would of course indicate the sequence. Okay. So, it goes through SM5, it does not hit any and impinges on the grating. Okay. And it is a simple uncharged beam hitting the grating. So, on the grating it looks like a spot, a circular spot. We will come to this 2, 3, 4 relative positions later. So, this is where it comes, goes to SM3, which is a circular big mirror. From SM3 it goes to SM4. From SM4 it comes back to SM3 and hits the grating once again. And in a correct alignment, if your alignment is perfect, then this beam number 2 should hit the grating lower than beam number 1. That is point number 1. Point number 2 is, so far it has done one hit on the grating, right. So, since it has hit the grating once, it has been dispersed. So, beam number 2, which is directly below beam number 1, spot number 2 let us say, is no longer a circle. You see a stripe, a streak. Has somebody seen when these guys opened up? You have seen, right. So, this is actually a streak, it is not a circle. Then, okay, this is 1, this is 2, it goes back here, then back to SM3, then it hits the grating above spot number 1 and it is still a streak. Then from here it goes to SM6, sorry, I think I got it a little wrong, 1, 2, from 2 it goes to SM5, SM6, back to spot number 3, comes to SM3, goes to SM4, comes back, and then when it, the last time it hits the grating, that dispersion is gone, because so many passes, again well, dispersion is still there, but you do not see a streak anymore, once again you see a nice circular spot, and that is what goes to SM7, and from there it moves out. So, this is the stretcher we have in our laser. Where we have in our laser, we will see in our amplifier, and this is the compressor. Once again, the compressor has only one grating. Earlier I have shown you a design with 2 gratings, right? But here, since it is a one box laser, everything has been made very compact. So, minimum number of optics has been used. So, instead of putting another grating, what they have done is, here it is perhaps not very clear about what it happens here, but once again there are several passes, and here you can see the relative positions of the beams 1, 2, 3 and 4. Once again, the first beam that goes in is circular, second and third are streaks, fourth one is where the spatial dispersion is taken care of, but not spectral dispersion, and that is beam number 4, which goes out. Okay. This is what we have. So, that almost concludes our discussion of stretchers and compressors. But then I might have given you the impression over the course of this discussion that if you want to stretch a beam or if you want to compress a beam, all that is there at your disposal is grating or prism. So, you will see in literature designs using not gratings, but prisms. Okay, that is understandable, but that is not the only thing. In fact, whatever technology we have is moving towards miniaturization. So, I think the latest development in this field is something called VHG, solid glass volume holographic grating. So, you remember we talked about the Bragg mirror, right? Bragg mirror, where reflection is from different layers. Here also what you have is, so this is a very small device, and so far I do not know if anybody else does it. There is this company called Ondax, which has now been taken over by Coherent. Ondax markets this, and the principle was known long ago, and in fact when this was demonstrated long ago as well in 1987 optics letters paper. But then now this company has developed it and marketed it as a product, and it is very simple. What you have is, you have an optical fiber feeding the pulse into it, and what is it that we have to remember if you are going to use optical fiber in an application like this? You better use a polarization maintaining fiber. It is very important, and in the next module we will see how we use polarization very effectively. So, typically what you have is, you have this fiber going in. If it goes in through here, then there are since it is a holographic grating, there are several reflecting surfaces, and different reflecting surfaces reflect different frequencies. It is as simple as that. So, red gets reflected first, followed by green, followed by blue. So, if your input was a broad pulse, charped pulse, provided the charp is such that red trails and blue leads, then this kind of an arrangement is going to give you a compressed output. Otherwise, the sequence of reflecting mirrors has to be opposite. But the good thing here is that if you take a pair of these VHG stretcher and compressor, all you have to do is put in the pulse, the initial output of the oscillator, uncharped pulse, you put it in here, let us say. Then what will happen? You get a charped pulse, and you get a charped pulse in which red leads and blue follows. In the compressor side, just turn it around. Let the beam going from here and not from here. Then what will happen? Then it will get compensated. So, the same piece of optic can be used either as a stretcher or as a compressor, depending on which is the input, which is the output. And I have not seen it, but from the pictures on their website and all, it seems like something that is about this size. So, the stretcher that I used 20 years ago was about this size. square. The stretcher we use now is about this, maybe this, and the one we are talking about here is this. So, that is what advent of technology and miniaturization does. Okay. So much for pulse stretching and pulse compression. We are going to next discuss the actual amplification bit of chirp pulse amplification method.